So, welcome to Virtual Machine Introspection to detect and protect. I see people standing in the back. I would recommend everyone to move forward because usually it gets a little crowded as the talk goes on. So what this talk is going to cover, I will talk about why I care about virtual machine introspection and why should you. I will introduce Zen a little bit, and then we'll dive into virtual machine introspection and the three aspects that we will cover today are isolation, interpretation, and interposition. We'll have some demos. Hopefully you will be able to see it, though the projector is quite crappy, so we'll see about that. And then I will release some publicly some new tools, so it's worth sticking around. So why I care about this topic is it's my PhD topic, so I'm using this technology to develop malware collection and malware analysis tools, mostly dynamic malware analysis. And also last year we received a generous grant from DARPA through the Cyber Fast Track program to develop a cloud IDS prototype. And the prototype was successful, and we had been invited to present it at the DARPA demo day at the Pentagon earlier this year. And this very same tool will be released today. Also, this topic is an up-and-coming field. It's mostly being covered in academia, but it is rapidly maturing, so it will be available commercially probably in the next couple of years. So let's talk about cloud security a little bit. We had a nice keynote today that touched upon some of the aspects of cloud security, so I hope to pick up the thread where Jason left it off. Some of the assumptions that people make about virtualization and cloud security in general is that, well, I have a virtual machine, I'm safe, right? I'm running this, who knows what type of software in VirtualBox, in Zen, nothing can go wrong. Also, if you have a base API in your Amazon instance and most of your instances are running in short period for 2 weeks and then you wipe it, why would you worry about whatever breaks in there? It will be wiped next time, maybe in an hour, maybe in 2 days, so risk is low. It's not really worth the cost of overhead, or just simply not going to happen to me, or you would think that you can use your existing tools and it will just work. And these assumptions are unfortunately wrong, but with your existing tools you might get some benefits, but it's not perfect. For example, if you run your standard antivirus or host-based IDS system in a cloud instance, the problem is that there is really no isolation between what you're trying to protect and what is doing the protection. So for example, Netflix uses OSSec, which is an open source host-based IDS system, which just 2 weeks ago had a local privilege escalation bug, which is kind of hilarious when your system that you're trying to protect is exploited through the system that is doing the protection, right? That's the latest hack you can have. So that's bad. Then you could use network IDS, snort, but then you have limited or no context on what is actually happening, especially if things are encrypted. You don't really know what's going on. Some vendors have started using tools that scan the VM's disk to look for signatures or even scan the VM's memory, but then you don't really have interposition. It's a totally passive type of scanning. But it's better than nothing, right? But if you think about it, there's a lot of benefits that you can take of hypervisors and virtualization in general. Most importantly, you can move out your security stack from the domain that you're trying to protect, right? So you can have a hypervisor-based isolation on your system, and you really can see everything that's happening within your virtual system. You can take a look at the virtual hardware and interpret what is actually happening, what processes are running, what users are active, connections, files, everything. Furthermore, it's an actively running system, and you can really trap everything that you want within that system, and you can have active monitoring and control over that system. So you really have interposition. So that would be an ideal cloud system, right? So if you look at Zen, or how Zen is implemented, it is called a bare metal virtual machine monitor. So it's running in VMX root directly on the hardware. There's a very minimal interface that's exposed through hypercalls, which are very similar to system calls, but it's very minimal, and Zen is really not bloated yet. Everything else is running in a domain, which is called DOM0 in Zen's terminology, which is a privileged domain. Everything else is deprivileged VM. That's where you run your applications. So now let's look at isolation. In Zen, we could move the security stack into DOM0. That would already move the security out from the virtual machine that you're trying to protect into a separate virtual machine. But you could also just move it into a separate domain outside of DOM0, which you can do on Zen because Zen allows for advanced disaggregation and role delegation. But there are some problems, of course. So the way access control actually works in Zen is threefold. The most important part is called Zen Security Modules, which was contributed by the NSA. And it is disabled by default, so if you're paranoid about the NSA, it is not the default mode of Zen. But it is very important because this is what really allows for advanced disaggregation of Zen. Unfortunately, it's only usable since like last year, so version 4.3. So when we actually started the DARPA project, this was a very first step that we proposed to do is move the security stack into a separate security domain. But of course, it was unusable at that point. But fortunately, the NSA was just contributing that patch, so everything worked out well for us. But as we were using this new NSA feature, we discovered that access control is not only happening within Zen, but even in the Linux kernel itself. So there are some convenient kernel drivers within the Linux kernel that allow you to issue hypercalls. These are totally convenient kernel drivers that you can use. You can issue hypercalls separately, but you probably don't want to do that. But if you use these kernel drivers, what we discovered was that the kernel itself was checking if it was DOM0 or not. So even though Zen would allow us to issue hypercalls, the kernel itself running in a secondary control domain was refusing to execute those hypercalls because it was in DOM0. So that was the very first patch that came out from our project. We patched that in Linux 3.8. So starting from Linux 3.8, you can actually have secondary control domains running on Zen with custom permissions to control other domains on the system. The third aspect is called Zen Store. Now, this is something very Zen specific that most people probably don't know about. It is pretty much Zen's registry, where a lot of the meta information about domains is being kept, like the domain's name. For example, the hypervisor doesn't really care what you named your domain, right? It's totally arbitrary. So why keep that information within the hypervisor? It is offloaded into Zen Store. And then Zen Store has its own access control system, which is totally separate from everything else. So we can just ignore it, right? We don't care about what the domain's name is. If you have the domain's ID, that's really all that you need to get going. So if you look at this picture, this is what, starting from Zen 4.3, is possible. So you can have a separate security domain working in tandem with a custom XSM policy. Now, XSM is essentially like SE Linux. You have a policy that is enforced by the hypervisor, and then you can have a security domain that can monitor all of your virtual machines on the host, or you can have it monitor a single one or any combination, right? Which is very important because if you think about it, that's what multi-tenant cloud deployments are. You have many different people using the same hardware, and security doesn't necessarily mean the same thing for everyone on the same hardware. So you want to possibly have multiple security domains that don't control everything on the system, like if you run your security stack in DOM0 that controls all of the virtual machines, which you probably don't want to have. So you can have custom security domains, which are not as powerful as DOM0. So even if you have some exploit within the security domain, like how it happened with OSSec, if an attacker exploits that system, it doesn't gain control of the trusted computing base, the TCB. It only gains access to another virtual machine within the system. Everyone else is safe. The second aspect of virtual machine introspection that's probably the most important part is really understanding what is happening within those virtual machines. This area very heavily overlaps with forensics memory analysis, like volatility. If you're familiar with it, we have some Hello workshops going on that teaches volatility, so I recommend taking a look at those. Essentially, what is going on here is that you take a look at the virtual hardware of those domains running, mainly the memory and the vCPU registers. So if you look at the memory of a virtual machine, what you're going to see is physical, semi-physical memory that the guest operating system sets up. And to be able to map out what is happening inside, you need to understand paging, right? All of the operating systems that you run in the cloud have some sort of paging, either 32-bit or 64-bit paging, and you need to understand how is that memory mapped into those processes. If you just look at the raw memory, that is just going to be a flat memory, and you're going to have a hard time finding out what is really happening. You have a lot of noise in there. And then you want to understand what the operating system is actually doing, so the most convenient way for that is using the operating system's debug symbols. So that's what volatility is doing, for example, as well. So the tool that we started working with is called LibVMI. It comes out from a PhD thesis from Georgia Tech that was really designed to support multiple hypervisors while being a transparent abstraction layer to achieve effective VMI. It supports right now Zen and KVM. The Zen side is probably a little bit more mature because it grew out from a previous library called XenXS, but it also supports KVM, and potentially we will add other hypervisor support in the future. It also supports pretty much all of the paging systems out there today, so all of the x86 and 64-bit paging modes. And recently, we also added the ARM paging mode to it, so you can actually use this library now with Zen on ARM. And it also supports Windows and Linux. We also use Recall, which is a public fork of Volatility by Google. It's a pretty recent one, but it's a very nice framework, which generates really nice debug profiles for both Windows and Linux, which simplifies our life a lot because Google gives support for it, and we don't have to. So, and of course, it does another. It's a forensics framework, so it does a lot more than that. But this is what we really care about for now. We'll talk about a little bit about Windows forensics here, but keep in mind that when you're running in the cloud, you're probably going to be using Linux. But a lot of the topics that I will discuss here are applicable to Linux as well. So when you're starting to looking at the memory of a virtual machine, the first thing you want to do is locate the kernel within that physical memory. And the way Volatility does it, for example, it simply does a brute force search. There is a magic string, 4 letters, KDBG, and it just scans for it, which of course means that it's easily hidden and there are lots of false positives. The way we use Recall and LibVMI is that we have access to the virtual hardware information through the registers as well, which is an advantage that Volatility can't afford. So if you look at the vCPU 0, on Windows 7, for example, the FS and GS registers point to this special area called the kernel control region something, processor control region, which is, of course, has a offset associated within the debug information. So virtual machine introspection in a lot of aspects is a lot easier than forensics memory analysis because we have really access to the hardware. Furthermore, this information is binding, so malware can just relocate this information, otherwise Windows will crash. So this is binding information, so you can actually trust it, which you can't really do with a lot of things when you only have access to the memory. And then if you want to map out more detailed information about what is happening within the operating system, the way Volatility does it, for example, is uses this in-memory debugging structure, essentially, to find where the list of running processes are, kernel modules, which can be, of course, obfuscated because it's a non-essential part of the kernel. And in Windows 8, it's actually heavily encoded. So Windows really doesn't want you to look at this unless you have the proper tools, right? If Windows crashes, that's when you want to look at it. It's not designed to be accessed through a hypervisor. Now, with LibVMI and recall, we can use the pre-generated debug symbols, and we should be fine. And it works directly on Windows 8 64-bit as well, because that information is binding, right? Microsoft gave us those debug symbols, so we can trust that it accurately describes where those structures are going to be in memory. But again, this is a different attacker model than what forensics tools do. Usually when you're using forensics tools, you probably have a memory image that is already corrupted. Something is already bad in there, someone gave it to you, you need to find out what went wrong. With virtual machines, you have the assumptions that you start monitoring preferably before you are already owned. If you're starting to monitor a system that is already owned, there's not much you can really do. But potentially, if you start early enough, you have a chance to step in and stop being exploited. Now, interposition is a little bit trickier because, as I said previously, scanning VM memory is good, and it gets you a lot, and even is effective against rootkits. Like, for example, volatility's full text scans are very good, but they are not really bulletproof. So those informations that scans use are not binding information. And furthermore, you have concurrency issues, right? You scan the memory of a live virtual machine. By the time you finish scanning the raw physical memory, things have already changed from the time you started. So how do you really know what's going on? So you need interposition, where you step in and you pause the execution of that vCPU or the entire domain to have a coherent view into what's happening. So what that means is that you need to induce and trap VM exits. So VM exit is an instruction on the Intel CPU that tells the hardware to transfer the control from the domain to the hypervisor. And that's really what you want to do when you are implementing a security domain. You want to trap events that you say that, okay, this is critical, I need to step in and inspect what is happening if I want it to happen. So the hypervisor needs to forward those events to your security domain. And Zen, in that respect, is very nice because there are a lot of instructions that you can use to induce these traps, and Zen has the system to forward those to your security system. So the instructions on the top are the Intel instructions that automatically trap into the hypervisor. So if you execute any of those instructions, it will go into the hypervisor. But you also have, in modern CPUs at least, you have really a plethora of options that you can configure within the hypervisor to tell the hardware when to transfer control back to the hypervisor, which is great because this was the case a couple years ago. And of course, this is just a short list. If you want to look at the entire list, look at the manual, there's a lot more. So right now, Zen and LibVMI traps 4 types of events, which, as you can see, is a subset of all the events that you can do. But even just with these 4 types of events, you can do a lot. So for example, there are instructions called move to CR registers. These registers are used by operating systems to control different aspects of the hardware. Like, for example, when a new process is being scheduled, the CR3 register gets the physical address of the page tables to do the virtual to physical translation. It is trappable to the hypervisor. Great, we can tell when a new process is being scheduled within our operating system, and it's invisible to the operating system. It doesn't know that you trapped and it was paused. Same thing with other CPU features like SMAP, SMAP. You can trap when it's enabled or disabled. You probably don't want some malware to disable protections on your vCPUs. And you can also trap TLB flushes and a lot of other stuff. So these are very convenient events to trap. The second set of events that's very important is called EPT violations. Now, EPT is a new virtualization feature that Intel added like 6 years ago, which adds another layer of paging. It's called extended page tables. What that is essentially is another set of address translation tables that the hardware can automatically do on your behalf, because the guest operating system thinks that it's running on real hardware, so you need to translate virtual memory to guest physical memory, and then guest physical memory to host physical memory. So there's a lot of translation going on. It's very slow if you have to emulate it. So Intel added this feature to speed it up. But what that means, though, is that you have a second address translation layer where you can just have totally different access permissions than the first layer. And what's even better, the second layer address translation faults into the hypervisor. So if you want to trace something invisibly that's happening within the guest, you just remove the flag that allows reading, writing, or executing from that page, and you will get the event. Only caveat is that you need to reset it after it's hit, otherwise you won't get subsequent events. But it's not a problem. We have invisible single stepping now on modern CPUs called the monitor trap flag. What that means is that you can actually instruct the hardware to trap into the hypervisor after a single instruction is executed within the guest. Of course, performance hit of that is huge if you just want to run everything through single stepping. You're never going to get anything done, but it's a very nice feature to have, for example, when you need to reset an EPT trap. And then the fourth type of event is the debug events. So there's a couple specific instructions on Intel for debuggers, right? You have a software, you want to debug it. There's a special instruction that your debugger injects into the code sections where you want to have breakpoints. And what we are using with LibVMI is called the int3 instruction, which is essentially just hex cc. You can inject that into the guest anywhere, and it will trap into the hypervisor. So with that, I want to do a couple demos, because that was a lot of high-level stuff. I want to show what this actually means in practice. Since the projector is really crappy, I put the videos up on YouTube. I recommend, if you have your laptop and your phone or whatever, to try to watch it there, because you're probably not going to see much. I'm going to have the link up on the upcoming slides, so you don't have to rush to write it down. Or you can just trust me when I describe what is actually happening. So here I have a Windows 7 virtual machine running on Xen. And, well, you probably can't really see what's happening there, but I'm just going to tell you what's happening. So this is Xen 4.4, and I have 2 domains. This is, right now I'm running the security system in DOM0, so this is not what you would have in production, but for the sake of this demo is good. So as you can see, you can list all of the processes in DOM0, what's running within the virtual machine, which you can see there is a lot more processes running than what Task Manager actually tells you. Similarly, you can list all the kernel modules. This is Windows, and those are all the kernel modules that you have loaded. So this is pretty standard stuff, not new here. But what I want to show here is really how to trace the execution of Windows using the debug information. So what you see there on the left is actually all of the system calls that are happening while Windows is executing. And as you can see, I can move the mouse around through VNC. And it is quite responsive, but as I move the mouse around, there's a lot more events spinning by. And it's totally impossible to see what's happening there, even if the resolution wasn't crappy. But let's try to cut through that noise, and I will show you a couple of things that are happening. So right now, I'm grabbing for instruction pointer that tells me what functions are actually called within the Windows kernel. So here, I'm not actually trapping the system calls. I'm trapping the internal kernel functions that result from the system calls. Another thing that I'm trapping is heap allocations within the Windows kernel. And as you can see, even when Windows is idle, there's a lot of heap allocations that are happening within Windows. And if I move the mouse around, I think I will move the mouse around. Right, that's right. There's even more heap allocations that are happening. So this is pretty cool. And it's really quite responsive, either though it's going from DOM0 back to the domain as it's executing. So why we care about heap allocations is because a lot of meta information that you care about in security happens through heap allocations that we can track. So for example, I can track all of the files that are being accessed within Windows before they are even accessed. So these are all the meta information that Windows allocates to open files. So I just opened up, I don't know, personalization, and these are all the files that are being opened by Windows. Or folders, right? Even folders get file objects allocated on the heap. And as you can see, this adds some overhead, but it's still quite usable. And this is not even optimized. So right now I'm just creating a new file on the desktop. And there we go, the new file shows up. And a lot of other files are being opened while this is happening, so this is great. If you want to debug an operating system, this is really awesome. But from a security perspective, you probably want to track what files are opened or executed. So for example, here I have the test.txt opened, and I added the txt extension on the desktop, but Windows adds it automatically. So I should probably not have done that, but there we go. So you can track all of the files that are opened within the virtual machine. So this is great if you have some sensitive information that you want to make sure is only accessed under certain circumstances, right? Or even if you want to check what files were dropped in Windows, it will show up here. Another important feature of that, if you track heap allocations, is if you think about DCOM attacks. So DCOM is a very basic rootkit technology that has been around forever. It is the abbreviation for direct kernel object manipulation. So the basic idea is that you have a linked list, for example, that holds all of your processes. So for example, if you open Task Manager, it will walk the process list, which is just a doubly linked list within Windows that holds all of these eProcess structures. And if you have a malicious process that you want to hide from the user, if you unhook that process from the list, it will be invisible to the user, but it will still execute, because Windows doesn't care about this list. It only cares about what's schedulable. But this is good against the user. But if you think about what we have just seen, if you track all of the heap allocations that happen, these eProcess structures are all allocated on the heap. So the problem really with DCOM is that if you walk this list, you won't find those structures. But if you know exactly where those structures are allocated on a heap, you don't even have to walk the list. So all of the DCOM attacks are now defeated because you know where everything is. So there is no way the rootkit can just unhook itself. You will always know where those structures are hidden. And even more, if you know that there is a structure there, but you can't find it in the list, well, that's a red flag immediately. So rootkits probably don't even want to do that anymore because it just gives it away immediately. So let's do another demo. This has been all passive monitoring of the machine. But let's look at active stuff. So this time, this is a Windows 7 64-bit Service Pack 1 VM. And what I'm going to do here is actually hijack the execution of a process within that domain. So I have Task Manager running there, and I just printed out the list of what's happening there. And I'm going to trap when Task Manager returned from kernel mode into user mode to execute calculator. And this has all happened from DOM0 without having any internal guest agent within the machine that you're monitoring. So what that means is that you don't even need to install anything within the system that adds to the attack base, right? You can use anything that's within the system already to do whatever you need to do with that system. So for example, if you need to execute a command, you can just commandeer any executing process within the machine and start up whatever command you need with the knowledge that it can't be hijacked because you control it from the hypervisor. So right now, I am going to inject a call to open Internet Explorer with some website of my choice, and it happens almost immediately. So this is a very handy feature if you're a sysadmin, right? You don't have to install anything within your system, and you can control it from the outside perspective. So when Amazon tells you that you are safe because they don't have the user credentials to your virtual machines, well, yes. That's true, but well, that's not gonna really get you much, because this is what you can really do with the hypervisor. So all of these tools that you have seen are actually part of a dynamic malware analysis system that will be published later this year at the ACSec conference. I'm actually releasing the tools here because, well, the name has some Hungarian connotations. I'm not sure if anyone gets the reference to what that is for. It's actually to a Hungarian sci-fi show. No? Well, I guess that's a good thing, because anyone remembers this? All right, so the story here is that my girlfriend dared me to name my system after something stupid like this TV show, which was probably the worst sci-fi show ever made. No? Someone liked it? Okay, sorry. Anyway, so they were, Drogfoops, I think, were some sort of aliens within that show. I don't even know how they look like. I don't think they showed them ever, but there we go. So it's now part of the history of computer science, the Drogfoops. So in conclusion, what cloud security really requires are new tools and new approaches to think about how you want to secure those systems in the cloud. And virtual machine introspection is no doubt one of the most important new tools that's coming, and it's maturing really rapidly to fill that gap. As you can see, dealing with rootkits is a lot easier when you have your security component outside from the domain that you're trying to protect. Many of the tools are open source, mostly GPL and LGPL, and patches are always welcome. And just to mention a couple things that's ahead is, as I said, VMI is a very important tool, but it's not perfect. There are some blind spots. For example, virtual DMA, if the hypervisor does emulation and the hypervisor gets compromised, well, VMI doesn't gonna get you much if what you're building on is compromised. And of course, the hypervisor is not really the root of the system. There are some other CPU modes or co-processors even that run on the same system that the VMM doesn't have control over. So for example, system management mode or AMT or ILO or whatever IPMI-based, co-processor-based system you have is not gonna really be affected by this. So ideally, you want to have control over those components as well to do some sort of VMM integrity check. And another field that's up and coming is Zen on ARM. I think the upcoming release in December is going to be the first Zen release that's going to be stable, called stable for ARM, which means a lot of the things that I just showed you will be available in your phone in a couple of years or even in your car. A lot of the car manufacturers are looking into using Zen. So this might be in your car in 10, 20 years, maybe sooner. And yep, I have been porting some of this into Zen already, so it's fun to work with Zen. I also want to give some shout out to some of the people who have been involved in this project. Most importantly, the Zentific crew that we did the DARPA project with, but also the volatility crew and the recall crew. They were all very helpful while we were developing this. And then, of course, Mudge, who did the entire Cyber Fast Track program at DARPA. There is a big thanks for him, because without that funding, I don't think any of this would be publicly available as it is now. So that was my presentation. I think I finished a little bit early, so thank you. And I'm not sure if questions are taken here or down at the corner, but since we have 10 minutes, I would take questions here, if there are any. Not? No questions? Everything was clear? Great, so you guys are awesome.